In this video, I would like to demonstrate the solution to exercise 5. In this exercise, you were asked to find the best polynomial fit to noisy data. The first cell already gives you the code to import all the libraries that you will need, then to load the data from a CSV file, and finally to print this data. Notice that the feature matrix is in variable x and the target vector is in variable y. So let's run this cell. And here you can see the data set. You see that we have a single feature, single target value, of course, and the data set is very noisy, which might affect the performance that we will measure, because noise is the error we cannot really reduce by improving the fit. So our goal is really to find a polynomial that will nicely follow this trend that we see in the data. So here is the detailed description of what we are asked to do in this exercise. First, we need to perform a stratified train test split. Then we need to create a polynomial model using pipeline. The next step is to use grid search CV to find the optimal polynomial degree and print out the best cross-validated score. Then we will calculate performance on test set. We will plot the fitted model and finally print out the coefficients of the model. So the question you are then asked is whether you can work out what was the underlying polynomial model, and hint you are given is that the coefficients were whole numbers. So let's see whether we can find out. Okay, so our first task is to do stratified train test split. So we already have here code to separate the features into bins, and we will want our training set and test set to have the same distribution of these features, so as it's in these bins. So let's start. So function that we need is train test split, train test split. And then first parameter I need to input is my training set, my whole set, so X and Y, so my features and targets. And then I need to say proportion of the data I want in my test set. So it's test size, and I say I want 20%, 0.2. And finally, I want to make sure that the distribution of features is the same in train and test. So I will say stratify by the bins. Okay, let's run that. And that seems to work fine. So now we need to create a polynomial model, and this model we already know is a pipeline of two objects. First one is the transformer object that will transform the features into the polynomial features, and second one is the linear regression. So let's do that, pipeline. And now I need two sets of brackets. And here I can write my first object, again within the brackets. So first I will name it. It's me choosing this name, and I will call it poly features. Then I will be able to refer to this object through this string. Okay, comma, and now the object polynomial features. And I don't really need to say the degree, because degree is something that we will find. So, comma, and now my second object in the pipeline, which will be linear regression. So, lin reg, that's the string I use to call my object. And then I will define the object linear regression. And now I wouldn't need to set the parameter, but I actually don't want to fit the intercept because polynomial features will create an intercept for me and I don't want to have two. So for that reason, I will set fit intercept to 0, to false. There we go. Now I need to create my parameter grid. So to do that, I need to create a dictionary. And first, I say the name of the parameters. This is very important because through this name, we will identify which parameters we are looping over, and that's the polynomial degree, right? Polynomial degree is a member variable of polynomial features. So that's what I have to say first. So I'll say poly features. And now polynomial features might have multiple member variables that are the parameters we want to make a search over, but we just want to do degree. So we need to say, and that will be 2 underscores to say which member variable we want, and then we write his name. Okay. So that's it. Now colon. And now we say what kind of degrees we want to go over. And we want to start at degree 1 and go up to degree 20. So I can just say I want range from 1 to 20. This this Python function will give me all the numbers from 1 to 20, the whole numbers only. Okay, so I didn't run this, so let me run that. So this code was fine. This code was fine as well. And now it's time for the grid search. So first I need to define this object. So grid search CV, because I want to use cross-validation. And now I will start with estimator, my model. And here I see I called my model pipeline. Okay. And next I need to put the parameters. That's what we defined here. And the final thing, I need to put how many folds I want. I want 5-fold cross validation, so I put CV equals 5. Okay, so now we need to perform the search, and that will be function fit. So grid search dot fit. And here we will say to which data we want to fit. And we want to fit to the training data only. So X train, Y train. So this command will fit the model, and now we can extract this best model. And the best model is saved in the variable best model, best estimator. Okay, so this should be it. So if you've done that correctly, there is a code to print out the best score and best polynomial degree. So let's see what we will get. And we see that the best score was 0.51 and best polynomial degree was 3. So let's check whether this makes sense. So if we look at the data, we have this type of shape, which does suggest third-degree polynomial. So I think we can be happy with that. And also we see that the data is very noisy. So perhaps that's the reason why our cross-validated score is so low, only 0.51. Perhaps there is very large error that we cannot really improve by finding a good model. So let's say we are satisfied with what we found. So the thing to remember now is that we save this best model in this variable best model. So it's called best estimator here, and we call it best model here. So we can use now this model, this fitted model that the grid search CV have found for us when we calculate the performance and plot the model. So our next task is to calculate the performance on test set. And we said we can use best model, where we saved our model found by gridsearch CV. And it will be function.score. And we want to calculate on test set. So X test, Y test. And the code for printing is there. So we run. And we got R2 score 0.64, which is higher than the cross-validated score. So you can see that sometimes it might be that the performance on the test set is actually better than even on training set, because it really depends what type of data ended up in the test set and what is their noise or irreducible error. And sometimes it might happen that test set has less error than the original training set. So that is okay. Okay, so now we need to plot the fitted model. So first, if you want to plot a curve, we need to sample the feature space. So let's see what kind of features we actually have. So if you look at this plot, we see that features go roughly from -3 to +3. So we can simply sample this interval. And for that, we will use function, numpy function np.linspace. And we want to go from -3 to +3. And we can say, for example, 100 samples would be good. And we need to, because this is a one-dimensional feature space, we always need to reshape to a matrix. So reshape -1, 1. Okay, and then Scikit-learn will be happy with it. So now we predict. So it's our best model again that we want to use for prediction. Predict. And now we predict on this feature space, so X curve. That's it. And now we need to plot. So first we plot training and test data. plt.plot X train, Y train. And I need to put a marker, which will be a circle. So O, because otherwise it would join the data, which is not what I want. So I say I want circles. plt.plot X test, Y test. And again, I need to put a circle. And finally, I want to plot the curve. plt.plot X curve, Y curve. And here I want a line for the curve, but I want to say the color that I wanted red. You can choose whatever you like. And I also would like to increase the width a little bit so that it looks nicer. So line width equals 3. That will give me a thicker line. Annotations already here. So let's plot. Perfect. It all worked, and you see that the shape really does correspond to the trend. So we are happy with what we plotted and what we selected as a model. And now our final task is to find out what are the coefficients of this model. So because the best model is really a pipeline, we need to extract the right object from it. So best model. And now to get to the linear regression coefficient, we have to choose the linear regression model. So we have named steps. And here is where we can access our linear regression model through the name we gave it, which was linreg. So if you look up here, when we created the pipeline, right, is this second object, linreg, that's how we called it. And we see that it's linear regression. So if we do these name steps, and we choose linreg, then we will have a linear regression object, and that has a member variable coef that will give us the coefficients that we're looking for. So let's print them. And also I rounded them to the whole numbers because we said that they would be whole numbers, and these are our coefficients. So now we can answer this question. So the coefficients will always start from the 0 degree all the way up to the 3rd degree. So it will be 2 plus, actually not plus, minus 3 x. Now quadratic term is 0, so we don't need to put it, and cubic term is 1. So plus x cubed. That's it. Run it. I have my answer, y equals to minus 3x plus x cubed. So that's the underlying polynomial from which these data were generated. So there is one more thing that I would like to say about this. This data is noisy, and train test split is always random. So it could happen that you will get a higher degree polynomial as a solution because there is some randomness in it. So sometimes the coefficients of the higher order will be very small. So when they are rounded, they will become zeros. So we will still see the shape, but you can also rerun the code again because there will be a new random split, and then you can check whether you get 3rd degree polynomial. But you should always get to this solution.